So we're looking at something called as principle of conservation of mechanical energy. Again, this is related to kinetic energy and potential energy, and we have kind of seen this few times, but now officially we are getting introduced to it. So basically, imagine energy as a kind of cosmic currency. It can take many forms. So it can be in many different places. It can be energy of motion or energy of position, or even energy locked up in atoms, right? So there are many ways, right? Energy can be stored in many ways that we have seen. Mechanical energy is like a specific bank account that only deals with two types of currencies, kinetic and potential. So first thing that you guys have to be very clear with this, with the following, is that we are dealing only with potential energy and kinetic energy. If there is no outside influence like friction, heat and all that, the amount stays the same. So let me put it this way. If the interaction between, if the forces or the energy, the forms of energy is only two, kinetic energy and potential energy. If I have 102 rupees and say 34 rupees, after some time I can see that this has reduced to 34 and this will be 102. After some time I can see say 100 and this can be 36. This can be 0 at some point of time and this can be 136. This is how it would be, is what your principle of conservation of mechanical energy tells. Let's look at the official statement. The definition is that total mechanical energy, that is the kinetic energy plus potential energy of a closed system, remains unchanged as long as only force acting are conservative force. Okay, so we have a small proof, we'll do that. But let me show this actually. We have seen this. We have a bouncing ball and we have a graph. Okay, so let me, yeah. Can you see that? At the bottom, the potential energy decreases and at the top, kinetic energy decreases. Right? You have to observe this. Observe that mechanical energy remains the same. That's the third thing that we need to observe. Whatever you do, if this happens, there are a lot of things that we are ignoring over here. But if it happens, if that condition is maintained, that we are just dealing with potential energy and kinetic energy and other things are to be ignored, then this is true. That is, the mechanical energy will remain constant. Okay, guys. So let me, no, I have to open this. Right, guys. So let's look at the proof. We're looking at the proof, guys, now. So we'll consider an object. It undergoes a displacement of delta x or delta y, whatever you guys want to call it as, under the action of a, again, this is generic, okay? This is not per se directly, it's not just only your gravitational energy we are dealing with, this is general. Then from work energy theorem, you remember work energy theorem? So we are looking at change in kinetic energy is equal to work that can be written as force into displacement, right? Both are, remember, this is work. Now, as the force is conservative, like we are in specific dealing with conservative force, then delta U will be the negative of the work done. So delta U is minus f of x dx, right? Now if I happen to add 1 and 2, what is 1 and 2? This is 1 and this is my 2. What will we get? Delta Ke plus delta U is equal to 0. What does delta Ke mean? Final minus initial plus delta U mean potential energy final minus initial. So if I rearrange, kinetic energy final plus potential energy final is equal to kinetic energy initial plus potential energy initial, and that's your proof. That's it. So we got to see that with the bouncing ball as well. So that is your principle of conservation of mechanical energy. So basically anything that you're studying over here can be applied to all the conservative force. So this set of videos are pretty important. I'm sorry it is a bit dull. Even I felt that I'm not able to make it more interesting because this is pure words and maths and equations and stuff. It is sort of dry. Okay guys. So just take it as of now. As in when you apply it with numbers and derivations and stuff, it will make sense. Okay, now you have to copy this.